You know, black holes are probably the ultimate cosmic paradox. We're talking about objects with so much mass crammed into such a tiny space that nothing, not even light itself, can get out. And for decades, our best theories have told us that right at their center lies something impossible, a point with absolutely zero volume but infinite density. But what if that's not really the whole story? Okay, let's get into it.
I mean, that's the fundamental question, right? Einstein's general relativity, which is our absolute best guide to how gravity works, predicts that the core of a black hole is a singularity. But here's a little secret from the world of physics. Whenever the word infinity pops up in an equation, it's usually a giant red flag. It's a sign that our understanding is breaking down, that we've hit a mathematical wall. So, how on earth do you put a ruler to something that our own physics says makes no sense?
To even begin to solve this mystery, we have to throw away all our normal rulers. We need to go much, much smaller. We have to find the universe's most fundamental building blocks, the absolute smallest units of reality itself.
And our first clue comes from the incredibly weird world of quantum theory. It suggests that reality, might not be this smooth, continuous thing we experience. Instead, if you could zoom in far, far enough, you'd find that space and time are actually pixelated. They're made of these tiny, indivisible little packets called quanta.
And these fundamental pixels of our universe, they actually have names, the Planck units. These were first proposed by the physicist Max Planck, and they aren't just some arbitrary numbers. Nope, they represent the absolute limits of measurement. You've got the Planck length, the shortest possible distance that can exist, and the Planck time, the quickest possible tick of the cosmic clock. If you go any smaller than this, physical reality as we know it just ceases to have any meaning.
Just to give you an idea of how mind-bendingly small this is, think about a single proton. We already consider that to be unimaginably tiny, right? Well, a proton is about 100 quintillion times bigger than a single Planck length. This is the absolute bedrock of reality we're going to use as our new ruler.
Okay, so we've got our new ruler, one based on the smallest possible size in the universe. But that's only one piece of this puzzle, because it turns out that space isn't just limited by its size, it's also limited by how much information it can actually hold. This wild idea is called the Bekenstein bound, and you can pretty much think of it as a fundamental law of the universe, kind of like a cosmic hard drive limit. Any given region of space, no matter what it is, has a maximum storage capacity for information. It can only hold so much.
So here's the crucial point. You can't just keep cramming more and more stuff, more matter, more energy, which is all just a form of information, into the same spot forever. At a certain point, the universe itself basically puts up a stop sign and says, sorry, this volume is full.
And boom, there it is. There's the conflict. General relativity predicts an infinite collapse, which would mean an infinite amount of information getting packed into a space with zero volume. And that completely violates the Bekenstein bound. So one of these fundamental ideas has to give. What is it that stops this supposedly unstoppable collapse?
Well, the solution to this paradox is absolutely astonishing. It's not some new, undiscovered force that suddenly slams on the brakes. The answer lies in a completely radical reimagining of what time itself is doing inside the black hole.
Okay, let's walk through this step by step. A star collapses, just like Einstein predicted. But as it gets crushed down, its density hits this unbelievable critical limit known as the Planck density. That's the absolute maximum density the universe will allow. And at this insane point, the fabric of space-time is so warped that the speed of light inside that region actually drops to zero. And if light can't move, well, then time itself stops. The collapse is instantly frozen, caught in one single permanent moment.
This gives us a completely new picture. The heart of a black hole isn't some infinite mathematical point. It's a frozen, collapsing star, an object literally trapped in a timeless state, balanced perfectly on the knife's edge of the laws of physics, which prevents it from ever actually reaching infinity.
Now, this new understanding, it doesn't just solve a deep paradox. It gives us a practical tool. It gives us a way to finally perform the measurement we've been trying to make all along. And this tool, which comes from these principles, is called the Left Cojecture.
And what the Left Conjecture does is it provides this beautifully elegant way to figure out the singularity's true size. It basically says that its volume is just a simple ratio of the black hole's total mass to that fundamental Planck mass. It creates this stunningly direct bridge between the biggest objects in the cosmos and its absolute smallest components.
So theory is one thing, but let's put this thing to the test, right? We're going to apply this formula to a very real object, Sagittarius A star, the supermassive black hole that's lurking right at the heart of our own Milky Way galaxy.
So we take its mass, which is over 4 million times the mass of our Sun, and we plug it right into the Left Cojecture formula. After the calculation, we get the true diameter of its singularity. It is 1.469 times 10 to the minus 20 meters.
Now that's a number so small it's almost impossible to wrap your head around. To give it some context, a single proton is over 113,000 times larger than the singularity of the supermassive black hole that our entire galaxy orbits. It is infinitesimally small, yes, but here's the crucial point. It's not zero. It has a real physical size. So what are the big takeaways from all this? First, singularities are not infinite mathematical oddities. They are real physical objects. Second, they have a measurable, even if it's minuscule, volume. And this is possible because the collapse gets frozen in time right at that Planck density. And maybe most importantly, this means the laws of physics are preserved. They aren't broken by black holes, they're just pushed to their absolute most extreme limits.
And really, this just opens up a whole new path forward. By redefining how we think about space and time, we found a way to measure the unmeasurable. And it leaves us with this incredible, tantalizing question: if the infinity at the heart of a black hole actually has a finite size, what other cosmic impossibilities are just out there waiting for us to find the right ruler?